What we're going to discuss today has a lot to do with how we can draw conclusions about different physical systems using symmetries. And I don't know if you remember, but last time, which was before the Easter break, we were discussing representations, and in particular, we were discussing what it meant for a representation to be reducible. Essentially, it meant that we could rewrite the representation as a representation on two separate invariant subspaces. What we're going to discuss or start discussing today is what is called irreps, or irreducible representations. So an irreducible representation is essentially any representation that is not reducible anymore. If you remember, I mean, when we were talking about reducible representations, we reduced a representation of, say, dimension n to two representations, each of a dimension lower. And of course, you cannot go on forever with this. At some point, I mean, for example, a one-dimensional representation, you can never reduce it, so all one-dimensional representations are going to be irreducible. So the basic definition of an irreducible representation is that it cannot be reduced anymore. And they will play a very important role when we discuss the physics. So just to say that in other words, then an irreducible representation is a representation you can call it raw, and I remind you that the representation is a homomorphism from some group to some linear operators on a vector space, such that for any vector v that belongs to this vector space on which we have the representation, this set that we can form by having the homomorphism of the different group elements act on v. So this set is going to span the entire vector space v. So that is to say that regardless of what this vector is, v, you're going to find a group element A such that this set of vectors is a complete basis for, or it doesn't have to be completely linear independent, it just has to span the vector space. Now, just one side remark that would be useful, and it is that if you have a finite group, so a group with a finite number of elements, they have a finite number of irreps. Which also means that if you have any representation of such a group, you can write it as a direct sum of those irreps. So given that you know what these irreps are, you can write any new representation that you find. You can write it as a direct sum of these representations. Let's look at an example. So we looked at S3, for example, this permutation group S3. So let's look at the representation of that. So the symmetric group of permutations of 3 elements. We can choose two generators of this group. So we pick the generators. And I'm going to pick the cycle switching 1 and 2 and the cycle switching 1 and 3. Now I just need to recharge the pen. Now, given that if I know how the representation acts on the generators, then I know how the representation is going to act on any element, because any element can be written in terms of the generators, which means that the representation acting on that element due to the homomorphism property can be written as the corresponding product of the representation acting on the generators. So I pick those two generators, 1, 2, and 1, 3. Using those two group elements, I can generate any permutation of 3 elements. So if I define the representation for those two, then I know what the representation is for any group element. And the representation that I'm going to choose is the following. So I'm going to let rho of 1, 2. I'm going to choose a 3-dimensional representation, and I'm going to represent it by simply switching the corresponding components. So what I want for the 1, 2 element of S3 is to swap the first and second component of the vector. And in order to do that, I will use this matrix. This matrix swaps the first and second component, and it leaves the third component invariant. And I will do the corresponding thing for rho 1, 3. So that will be keeping the second element in place and swapping the first and third components of the vector. So if I want to look at how this can be split into irreducible representations, well, we have in particular one vector here, which is the vector where I put all of the elements to 1. So we know that rho of 1, 2 acting on 1, 1, 1, that's equal to 1, 1, 1. Because since I'm just swapping the elements, swapping 1 and 1 leaves the vector invariant. The same thing, of course, goes for when I use the 1, 3. So regardless of what group element I use to act on this 1, 1, 1 vector, I get the same vector back. So this means that 1, 1, 1 spans here an invariant subspace. Of this representation. So that means that since regardless of what the element is here, I'm getting 1, 1, 1 back. It's an eigenvector of eigenvalue 1. So acting on this 1, 1, 1 vector with any of the group elements is going to give me 1, 1, 1 back. So the representation here is the trivial representation. So on this subspace spanned by this 1, 1, 1 vector, the representation is the trivial representation. And this is then an irreducible representation because it's one dimensional and cannot be reduced any further. Any questions? As usual, just stop me. Okay.
Sorry?
Yeah.
I can see that that vector belongs to an invariant subspace, but how do we know that it spans the entirety of it?
Because regardless, I mean, it is an invariant subspace because regardless of what group element I use here, it's going to be a product of those.
All right.
So, I mean, if I write an arbitrary linear combination of this, and it's well, just that because it's one-dimensional representation. An arbitrary constant of this is going to be invariant under any group transformation.
Yes.
Because any group transformation can be written as a product of those two.
Yes, I still don't quite see. Never mind, I'll think about it.
No, so I mean, this just means that the subspace is invariant, right? Because any vector of this form, that if I take rho and then I take an arbitrary element of A and I act on V, well, on let's say 1, 1, 1 now, because that's what we have. This is going to be 1, 1, 1.
I can see that. What I don't see is why that basis vector is enough to span the invariant subspace.
I mean, there might be several invariant subspaces, but this in particular is one. I mean, what it means to be an invariant subspace is just that if you take elements of this form, that they are going to be in the same subspace.
Yes.
So that is true. That's what an invariant subspace means. That if you act with any group transformation on a vector in the subspace, it should belong to the subspace. Then the subspace is invariant under the group transformation.
Thanks.
Okay, so we're going to come back a bit to how we can use those irreps. So there are a couple of lemmas that would be very useful later on, or in general are very useful to use in physics. They're called Schur's lemmas. And those are exactly statements about irreducible representations. Okay, so let's just state them first and then we discuss them. So the first of the lemmas is that I'm going now to assume that A is a linear operator on V, and that rho is an irrep on V that commutes with A. Now remember that rho, the representation here, we're representing group elements by linear operators on V. And so, I mean, A is a linear operator on V. It does not need to be the representation of any group element, but we do know what the notion of A commuting with rho means. It means that regardless of which group element you're representing, so let's say that we take rho A and A, that should be the same operator as A, rho A, for all A in the group. Then the first of Schur's lemmas says that A must be proportional to the identity. The lambda being a constant. So that if we have an irrep that commutes, or if we have an operator that on an irrep it commutes with the representation of all group elements, then it must be proportional to the identity on that subspace. Well, on the vector space of the representation. The second lemma is that if we have two inequivalent representations, or irreps rather, say ρ1 and ρ2 on v1 and v2 respectively. Now v1 and v2 can in general be different spaces, they can also be the same. The important thing is that ρ1 and ρ2 are inequivalent. And the linear operator B that goes from v1 to v2, and furthermore we want that B ρ1 of A should be equal to ρ2 of A B for all A. If this is the case, then B is necessarily equal to 0. So being inequivalent, well, if they are on different vector spaces, they are going to be inequivalent by default. But to say that two representations on the same vector space are inequivalent, well, let's say first what it means to be equivalent. Two representations are equivalent if ρ is equal to u ρ prime u inverse. We discussed this last time as well, just to remind ourselves. So u here is some linear operator that's invertible, and two representations are equivalent if they can be related like this. Okay, so I'm just going to go through the argument for the first. The argument for the second is a bit more involved and involves looking at more cases, more special cases. But let's look just at the first of Schur's lemmas. So what we wanted to show now is that is exactly so that if we have a linear operator A that commutes with the representation, then it must be proportional to the identity on this irrep. So in order to do that, let's consider now for a moment a vector V that is in this vector space which carries the irreducible representation. And I want now to consider eigenvectors of this operator A. So that means that just by definition of being an eigenvector, A acting on V is equal to lambda times V, where lambda is a constant. So what does this mean for the vectors we can create by acting with a group representation on V? So well, if I take A and I act on ρ acting on V, then I know that this is equal to, since A and ρ commute, this is equal to ρA A V. But V is an eigenvector of A by assumption now. So this means that this is equal to ρ of A lambda V. Lambda being a constant, I can move this to the left. So I get lambda ρA V. So if we look at what we have here now, this ρA V is equal to what is here, rho AV. So this means that also rho AV is an eigenvector of A with the same eigenvalue. So this means that all of the vectors of this form, rho times V, are eigenvectors of A with the same eigenvalue. And since they span the entire irrep, this means that all vectors in V are eigenvectors. Of A with eigenvalue lambda. Or put it another way, A acting on U is equal to lambda U for all U in V. So indeed, this means that A is proportional to the identity with this eigenvalue lambda as the proportionality constant. Any questions on that? So the proof of the second lemma is rather similar. It just involves that we have to check a lot more cases. And if you're interested in how it proceeds, we don't really have time to go through it now. It's in section 4.7.2 of my book.
Can I ask something?
Yeah, sorry.
So did we assume that V, like all V, was an invariant subspace of this row?
The capital V.
Yeah.
Yeah. So by assumption, V carries this irreducible representation, and therefore it is an invariant subspace under the action of the group. This is what we are using here to show that. I mean, this is the property that we need here. In this step.
Exactly, yeah.
I mean, if there were any other vectors in V that I could not write as a linear combination of those, then I would not have shown here that that A is proportional to identity.
Exactly.
But so it's exactly the argumentation that since we know that it is an irreducible representation, we know that vectors of this form span the entire subspace. And therefore, that this must be true. So let me just take a quick example of this. Oops. It may not be completely obvious, but I mean, so I'm going now to consider Eigen Functions of the Laplace operator. On the disk with Dirichlet boundary conditions. So that's essentially saying that, I mean, first of all, the set of functions that satisfy these boundary conditions, that's a vector space. And I can consider how that vector space is transformed under rotations. And since this operator, the Laplace operator, it's invariant under rotations, which is exactly saying that that it's going to commute with rotations. So if I rotate the Laplace operator, I get the same Laplace operator. Essentially, that if I have if I have some solution of the Poisson equation, which includes the Laplace operator, and I rotate that solution at the same time as I rotate the inhomogeneity, I'm going to get a new solution to the Poisson equation. So if we're looking at eigenfunctions, so let me take minus Laplace squared phi. I'm looking for functions of this type, right? And also that phi at radius 1 is equal to 0. That's the Dirichlet condition. Then, I mean, if you remember the mathematical methods, the eigenfunctions are of this form. So phi n L is going to be equal to j n alpha n L r e to the I n theta, right? Those are my eigenfunctions. And my eigenvalues are lambda, which is alpha n L squared. Now, I know that if I make a rotation, that it commutes with the Laplace operator. So if I rotate by an angle delta, and then apply the Laplace, it's the same thing as doing first Laplace and then the rotation. So this means that eigenfunctions with different lambda belong to different irreps. Of rotations into dimensions. This is a direct. It's a direct result from Schur's first lemma. And you can also you can see the dimension of the irreps essentially by looking at the degeneracy of the eigenvalues. I'm going to come back to that later as well. Okay, so now I'm going to go through a couple of things. It will not be immediately obvious how we will use them in physics, but the underlying theory is it's rather important. I'm not going to go through the proofs in detail here. I'm just going to sketch them because I will not have time to do more. If you want to have a look at them, you can look at them in the course literature as well. So the first theorem that I want to discuss is the so-called fundamental orthogonality theorem. For irreducible representations. So for any irreps, I'm going to call them rho mu and rho nu here. So mu and nu being just some number that numerates the irreducible representations of a finite group G. The following is going to hold. So if I sum over all group elements, I take rho mu IP of A, I take rho nu Qj of A inverse, then this is going to be equal to Ng divided by N mu. I'm going to come to what all of this means. Delta mu nu, delta Ij, delta PQ. So Ng here is the number of elements in the group. That's why I need a finite group. And mu is the dimensionality of the raw mu representation. So if I have a one-dimensional representation, mu, that is 1. If it's two-dimensional, it's 2, and so on. These deltas are just your regular Kronecker deltas. So this delta mu nu means that it's 0 if the representations are different. If mu is not equal to nu. The other deltas are just deltas of these indices that appear here. So in essence, this follows from Schur's lemma. This follows from Schur's second lemma. And essentially, what you need to do is that in Schur's second lemma, if you remember, we had this this operator B here. And what we do to show the fundamental orthogonality theorem is that we choose a very particular B, and it's going to be the sum over the elements in the group, and then raw mu of A. T is now any linear operator so far, and then raw nu of A inverse. So if we choose this B, so this will imply that we have exactly the situation that is discussed in Schur's second lemma. So if I choose this particular B, then I'm going to have exactly the kind of situation that we had in Schur's second lemma. So this is going to hold. That raw mu of A times B is going to be equal to B raw nu of A. So this means that then if mu and nu are inequivalent representations, then B must be equal to 0. So B is equal to delta mu nu. It's 0 if mu is different from nu. And if mu is equal to nu, then we have Schur's first lemma telling us that it's proportional to the identity. So then it's going to be lambda mu t. So some constant depending on t and the representation that we are looking at. And the particular choice that we can make here in order to obtain this fundamental orthogonality theorem is to choose that t, the components of t, so tij, is just delta I p delta jq. If we make this choice, then essentially what we recover is this formula, which is the fundamental orthogonality theorem. Any questions? No, it was a bit fast. Okay, so let me go through a second construction. So apart from this fundamental orthogonality theorem, I'm going to introduce something that is called characters. So characters are generally related to representations. So if you remember from last time, if we have, as long as we have a finite representation, we can represent it in terms of matrices, right? So the character, oops. Chi of a representation that's the trace of of this representation matrix. So it's defined as chi-rho of a group element A is the trace of the representation matrix. And one thing to note here is that the character is independent, or it's the same for all equivalent representations. So if rho and rho prime are equivalent, then we know that chi prime, so the character corresponding to rho prime, that's equal to the trace of rho prime of A. But since it's equivalent to rho, this is also equal to trace u rho u inverse for some u. And due to the cyclicity of the trace, I can move this inverse to the front, which means that I will have u inverse u, which is equal to 1, and then rho. So this is just trace of rho, which is the character of rho. So just as an example of this, let's consider the fundamental representation of rotations in 2 dimensions. So I represent a 2-dimensional rotation by an angle theta by this 2 by 2 matrix, which has cosine theta, sine theta, minus sine theta, and cosine theta. Then the corresponding character, so chi of this rotation by theta, that's the trace of rho theta, and the trace is the sum of the diagonal elements, so 2 times cosine of theta. For the trivial representation, so this up here was the fundamental representation. For the representation, then I'm representing all elements by the identity, and it's a 1-dimensional representation. So that means that rho, how am I going to call that here? Let me call it chi trivial of r theta. Well, it's going to be the trace of 1 because everything is represented by 1. So this is just 1. So you can see that in particular, this character has a very different, the character of the fundamental representation is a very different, it is very different from the character of the trivial representation. Just before the break, let me just discuss a few basic factor characters. So a few basic facts about characters. So first of all, the identity element, so the identity element of the group always has a character. Well, I'm always representing the identity element by the identity matrix in the representation. It's going to be the trace of the identity matrix of the representation, and the trace of that is going to be equal to the dimension of the representation. So if I'm representing on an n-dimensional vector space, then the character for the identity element is going to be n. Second, for a direct sum representation, we're going to have that chi1 plus 2. So if I have representation row 1 and row 2, represent the character of the direct sum representation, that's just going to be the sum of the individual characters. And that essentially just follows from the definition of the direct sum. And the same thing actually goes, but with the product instead, for the direct product. So up here we had row 1 plus 2, and down here we have row 1 direct product with 2. I'm going to have that chi1 direct product 2 of A is going to be chi1 of A multiplied by chi2 of A. And finally, the last fact that I want to go through is that conjugate elements, or it relates to conjugate elements. So if you remember what that means, it means that that two elements A and B are conjugate if there is some G in the group such that A is equal to G, B, G inverse. We're going to have the same character. Now, this is essentially, the argumentation is essentially the same that I used up here. So we know that the character of A is equal to trace of row of A, but that by definition is the trace of row of G, B, G inverse, and then we use that row is a homomorphism. So this is trace row of G, row of B, row of G inverse, and using the cyclicity of the trace, we're moving row inverse to the front. And again, the representation of the inverse is the inverse of the representation. So what we're left with is the trace of row of B, which is the character's value for element B. So any two elements in the group that are conjugate to each other are going to have the same value for the character. So often we're just going to talk about the value of the character on the conjugate class. So that will be the last thing I do before the break, is to discuss character tables, which is essentially a table of the value of the character on each conjugate class. So essentially, given a group, I can write down a table where I have the representations as the rows, and I have the values of the character as the columns. So what I do is that I do the following. I write the group that I'm making the character table for, and then I'm doing this. So I make a table and I write here row 1, row 2, and I can go on if I have several representations. And then I write on the horizontal, I write the conjugacy classes. The identity element always forms its own conjugacy class. And then I have other conjugacy classes A, B, there may be others. And typically I also write down the number of elements in each conjugacy class. And so in these entries here, I fill in the value of the character. So the value of the character for the identity element was always the dimensionality of the representation. So that's n1, n2, and so forth. Whereas I here put chi1 of A, so the value of the character of the representation 1 for conjugacy class A. And here chi2 of A, and so on. chi1 of B, chi2 of B. Are there any questions? So, I mean, after, yeah, sorry.
So if we have different representations on of the same group, then or if we have two different inequivalent representations, then are the characters guaranteed to be different? Since
yeah, I mean, if you have equivalent representations,
inequivalent.
If you have inequivalent, yes, they're going to be different.
Yeah. Okay, and they are guaranteed to be that.
I mean, after the break, we will see how we can use this, and we are particularly going to look at it for irreducible representations. Okay. And what we're going to do is that we're going to use these characters in order to see how a given representation can be irreducible representations.
Can you say the last thing again?
We're going to see how different representations, general representations, how they decompose into different irreducible representations. So we're going to use the characters in order to do that. Mm-hmm. I think it will become clear once we have discussed that, how we can use those to kind of see what irreducible representations a representation contains, essentially. Okay, I hope everybody's back. So I know that the last hour was a bit maybe theoretical. Let me first then start this hour by giving some further examples, discussing essentially what we ended with in the last hour. And then we'll go on to how we can use exactly what we were talking about in the end, how we can use the characters to deduce what kind of irreducible representations a general representation contains, and also how we can use that to deduce some physical properties of different systems. So first of all, some example. So I hope that you remember from last time before Easter, when I introduced representations. I introduced a representation in R3 of rotations in 2 dimensions. Essentially, what I said was I can just choose to represent my 2-dimensional rotations by rotations around the z-axis. And then I end up with a fundamental representation in the xy plane and the trivial representation in the z direction. So we saw that this led to a representation being able to be written as 1 plus ρ2, where 1 is the fundamental, the trivial representation. And ρ2 was the fundamental representation of 2D rotations. So this is written 1 plus 1O plus ρ2. So in particular, for the character then of this new representation, we have ρ1 plus ρ2, or rather, let me write it like this. So the character of this 3D representation of rotation by theta, well, that's the trace of cosine theta, sine theta, minus sine theta, cosine theta, and then 0, 0, 0, 0, 1. And you know that this is 1 plus 2 cosine theta, right? It's just the sum of the diagonal elements. But according to what we said here, this should be the sum of the characters of the representations that we split this representation in. And we can see that indeed, if we have chi1 of r theta plus chi2 of r theta, well, chi1 was the character of the trivial representation. So that's always 1. And we saw that this character of the two-dimensional representation, the fundamental representation, that was cosine 2 cosine theta. So indeed, we have this property that this representation, which is the direct sum of those two representations, the character is equal to the sum of the characters of the individual representations. Now, a second example before we go on, and this now relates to character tables, is that if we look at this symmetric group with three elements, so the group of permutations of 3 elements, the conjugacy classes of this group are, well, the identity conjugacy class, which just contains the identity, so making no permutation at all. And then we have the conjugacy class of cyclic permutations, which contains 1, 2, 3, and 1, 3, 2. And finally, we have the permutations that just switch 2 of the elements. And that is, I'm going to write it as sigma, and it contains 3 elements: 1, 2, 1, 3, and 2, 3. Now, let's go through 3 of the representations that we have here. First of all, the fundamental representation. We know that the fundamental representation has the character 1 for all group elements. So that's both of the identity, of the cyclic permutations, and of the permutations of 2 elements as well. If you remember, at the beginning of today, I introduced a 3-dimensional representation of this group. That was essentially just switching the components of this 3-dimensional vector. So for that one, we have a particular character. So for the representation that we discussed earlier, we have that row of 1, 2 was 1, 0, 1, 1, 0, was this matrix, and so on and so forth. So this means that chi of E for this representation, well, it's a 3-dimensional representation, and the representation of E, the identity element, is the 3-dimensional unit matrix. This is going to be 3. For chi of sigma, so this conjugacy class, well, that's actually exactly row 1, 2, right? So we just take the trace here, and we see that it's 1. And finally, for chi of C, that's going to be the trace, and then a cyclic permutation, which is going to look like this. So that's 0. But this means that we can also deduce, we saw that this representation contained the trivial representation. So we can ask, what is the character of the representation that remains? So for the representation, so we can call this representation row 3, this we call just row 1. For the representation row 2 then, such that row 3 is row 1 plus row 2. For that representation, we know that the character row 3 is the sum of the characters of row 1 and row 2. So that means that the character of row 2 must be the difference between the character of row 3 and row 1. So for that one, we will have, if we call these chi3s, and these called chi1s, then chi2 is going to be chi3 minus chi1. So that's chi2 of E. Well, it's a two-dimensional representation, and the value is 3 minus 1, so it's 2. So that's consistent. For chi2 of sigma, we have 1 minus 1, so that's 0. And finally, chi2 of C, that's 0 minus 1, so that's minus 1. Finally, I want to discuss one more representation here, and that's the even-odd representation. So even-odd representation, which is just row of E is row of C is plus 1, and row of sigma is minus 1. So essentially, I map to 1 for any even permutation, and I map to minus 1 for any odd permutation. And the characters of this, if I call this EO, it's a one-dimensional representation. So the character of E is 1, which is also the character of C. And the character of sigma is minus 1. Now, if I want to write down the character table here, I would write S3, and then I have 3 conjugacy clauses. I have E, I have C, and I have 2 elements in C, so I write 2C. And finally, I have 3 elements in sigma. We would have the trivial representation that had the value 1 on all conjugacy classes. We would have this row 2, which had the value 2 on E, had the value minus 1 on C, and value 0 on sigma. And the even odd is 1, 1, minus 1. And it's, as it turns out, I'm not writing down this 3D representation. And the reason for that is that all of those representations that I've written down here turn out to be irreducible. So I'm just writing down the irreducible representations here. Okay. So this is the way I can go about to write down the character table, for example, for this group. Any questions on the examples? Okay, so then let's move on to essentially to the last theoretical thing that we will discuss. And it's exactly what's going to allow us to draw physical conclusions using all of this framework that we have now developed. So if we look back to the fundamental orthogonality theorem, essentially what it told us, if we go back to wherever I had that, so we have it here, right? So let me just copy this. and go back here. So this is what we had. This is the fundamental orthogonality theorem. Now, I can now sum here. I put P equal to I, and I put Q equal to J, and I sum over I and J. So that's taking the trace of this row. It's taking the trace of this row separately. What's going to happen over here is that I'm going to get the sum over identity matrices. So essentially, if I do this, what I'm going to end up with is what looks like this. So I'm going to have ng, the number of elements in the group. I'm going to have that left. Delta mu nu. And then I'm going to have a sum over all of the group elements. And now, since I have the traces here of these matrices, those are just the characters. So this is the character mu on A, and the character nu on A inverse. And if we assume now that our representation is unitary, so for unitary representations, we have that chi nu A inverse is equal to chi nu A complex conjugate. This is rewritten as no, sorry, there should be an equality here. Otherwise, it doesn't make sense. For unitary representations, we can rewrite this in such a way that we have 1 over ng, and then the sum chi mu of A, chi nu of A star equal to delta mu nu. So I'm going to define this actually, this left-hand side. I'm going to define as chi mu, chi nu. So this is the character inner product between the characters for the representation mu and representation nu. So what this tells us is that if mu and nu are equivalent representations, this is 1. Irreducible representations. If they are equivalent irreducible representations, it's 1. If they are not, it's 0. So under this inner product, and by the way, this can also be rewritten if we want as 1 over ng, and instead of summing over the group elements, I can sum over the conjugacy classes, and then I get the factor of ki in front, and then I get chi of ci, chi nu of ci star, where now ki here is the number of elements in ci. So all I've done now is that I collected all of the contributions from the elements in the same conjugacy class since they have the same characters. So essentially what this tells us is that irreps are orthonormal. So we're going to be able to use this. So for any representation, so let's take a representation rho is generally going to be a direct sum of several representations. So I'm going to have n1 copies of row 1 and 2 copies of row 2, and so on. So if I have this representation, if I take the inner product of the character of this representation with the character of an irreducible representation, this is going to be n mu, which is the number of times. Actually, I already introduced a different. So this is going to be n mu, the number of times row 1 appears in the representation. So, for example, if this number would be 2, then the representation row 1 would appear in 2 copies in this representation row here. Okay. Any questions on that? This is essentially the last bit of theory that we will go through. I want to spend the rest of the time for examples. Okay, so let's go to examples. Let's look at the example of S3 again. So for S3, we had this 3D representation. And we saw that the character was that chi of E was 3, chi of C was 0, and chi of sigma was equal to 1. Now, if I want to take the character inner product, if I want to see how many times the fundamental the trivial representation appears in this representation, then I would check the character inner product of this 3D representation with that of the fundamental representation. And if you remember, the fundamental representation is 1 for all of them. So if we look at the definition here of the character inner product, I first need to divide by the number of elements in the group. And the group has 6 elements, so it's 1 over 6. And then for each conjugacy class, I add the number of elements in that conjugacy class multiplied by the values of the characters that I'm taking the inner product of. So if we start by E, there is 1 element in that conjugacy class, which is the identity. It has the value 3 for chi. It has the value 1 for the trivial representation. For C, we have 2 elements, but its value for this 3-dimensional representation is 0, and for the trivial it's 1. And finally, for the sigmas, we have 3 sigmas, and the value is 1 in both the fundamental and in the trivial and in this 3D representation. And you see that this equals to 1. So this tells us that this 3D representation, it is reducible, and it has 1 copy of the trivial representation because of this inner product. Okay, so we come to kind of the final example that I want to really discuss in detail. This might take some time. We have 20 minutes, so it should be fine. So a very useful application of everything we have discussed now, of all these symmetries, all this theory that we've been discussing, is to deduce what kind of different vibrational modes, for example, a molecule has. So the example that I want to take is vibrational degrees of freedom for ammonia. And I don't know if you remember your chemistry, but ammonia is NH3. And I'm going to try to draw it. It's not going to be super good looking because I'm drawing in 2 dimensions, and really ammonia is a very 3-dimensional molecule. So you have this this N molecule, and then you have kind of in an equilateral 3-sided pyramid, you have the hydrogen molecules. So first of all, we can ask ourselves, what's the symmetry group of this molecule? What kind of symmetries can we apply? And still get the same molecule back. So because of the way this molecule is constructed, it kind of has this 3-dimensional shape, like this small 3-dimensional pyramid. What we can do and still have the same molecule is that we can make rotations, which we can call C, by 2 pi over 3. But there is also a reflection symmetry in this direction, which we can call sigma. And as it turns out, we can number what those symmetries do by numbering the hydrogen molecules 1, 2, 3. We can also number the N molecule by 4. And any of the symmetry transformations is going to exchange the places of the hydrogen molecules and leave the nitrogen where it was from the beginning, right? So actually the symmetry group here is S3, the same symmetry group that we were just discussing up here. So the symmetry group is S3. So the question is, what kind of representation do I have when I want to discuss the motion, kind of the vibrational motion of this molecule? Well, each of the atoms here is going to have a small displacement vector from equilibrium. So in general, I'm going to be able to write out small displacements like this. And you see that there are generally going to be 4 displacements. So this is actually a 12-dimensional vector space, because each of the displacement is 3-dimensional. And the full vector space is then going to be the direct sum of all of those 4 displacements. And the question is, how does the symmetry group act on these displacements? So first of all, this symmetry group that we have here, it's a symmetry group of spatial transformations. It's reflections and rotations essentially in 3 dimensions. And each of those small displacements are going to be treated as 3D vectors under this spatial transformations. So I'm going to have 4 vectors that transform according to the spatial transformations here. And then I'm also going to exchange the vectors. So for example, if I do this rotation C, then 1 goes to 2, 2 goes to 3, and 3 goes to 1. So I'm exchanging in which position I have each vector. So it therefore turns out that this 12-dimensional representation is that rho of sigma. So I'm just going to write it down for sigma and for C. well, the representation itself is the direct product of R3 plus this 4-dimensional vector space. I'm going to just call it V4, which is where in which row I place each vector. So rho sigma is going to be represented by 1, -1, 1. This is just reflections in the XZ plane, essentially. So I'm changing the value of the Y component, and it's going to be doing that for each of these displacements. And then it's the direct product. So what happens with all of the vectors when I do this? Well, I'm keeping 1 in place. So this molecule is in the same place. So it's the displacement vector, goes back to itself. And I'm keeping 4 in place. But I'm exchanging the roles of 2 and 3. So the representation of sigma is this tensor product. And I can do a similar discussion for C. So C is a rotation by 2 pi over 3. So I'm going to have this rotation. So cosine 2 pi over 3, sine 2 pi over 3, minus sine 2 pi over 3, cosine 2 pi over 3, 0, 0, 0, 0, 1, because I'm rotating all of the displacements. And then I'm asking what atom maps to which atom later on. So the only one that's fixed is the 4. This is the nitrogen atom, which is in the same place, regardless of the symmetry transformation. And then I'm mapping 1 to 2. I'm mapping 2 to 3. And I'm mapping 3 to 1. So this is going to be the representation of C. So this means that I can now compute the character, right? Because the character of a product is the product of the characters. So I can write that chi of E, well, it's a 12-dimensional representation. So chi of E is 12. Chi of sigma, then I'm looking at this. So first of all, I have this, the character of this, which is 1, because the trace of that is 1. Let me write it out. It's 1 minus 1 plus 1. Multiplied by the trace of the second matrix here, which is 1 plus 1. 1 plus 0 plus 0 plus 1. So this is 1 times 2, so 2. And finally, I do the same for C. So I will have 2 cosine 2 pi over 3 plus 1 multiplied by 1. So just 1 plus 2 cosine 2 cosine 2 pi over 3. And that happens to be 0. So now I have the character for this representation, which means that I can deduce which irreps it contains by using the character table and the inner product of characters. So let me just write the character table down again. So for S3, we have the following character table. We have E, we have 2C, and we have 3 sigma. And now I'm going to call them slightly differently, but the trivial representation is often referred to as A1 with the character 1, 1, 1. Then we have this 2D representation, which is called E. Its character is 2 minus 1, 0. And finally, we have this A2, which is essentially this even odd representation, which has character 1, 1, minus 1. So I can now ask the question, which of these irreps does this representation contain, and at what multiplicity? So let me start by taking chi A1. And if I do that, let's check the time, we have 10 minutes. So I'm just going to go through it for this one, and then I'm going to write the result for the others. We had a character that was 12, 0, 2. So for our representation, it was 12, 0, 2, just to remember. So there are 6 elements in the group, so 1 over 6. And then 12 times 1, because there's one element in, there's one element in this conjugacy clause. This value is 12 and 1. Plus 2 times 0 times 1, plus 3 times 2 times 1. And if I did it correctly, this should be 3. So this means that this 12-dimensional representation contains the trivial representation 3 times. So it contains 3 copies of the trivial representation. And in the same way, I can compute chi E, and the result I will get is 4. And then chi A2, and the result is 1. So this means that this representation rho, it can be written as 3 A1s plus 4 E's plus 1 A2. Now let's check that the dimensions work out. So this rho was a 12-dimensional representation, and the dimensions of A1 and A2 are 1. So we have 3 plus 1, plus E was a 2-dimensional representation, so 4 times 2. So this is 12. So the dimensions work out. Now, this is not only vibrational modes, because we can also have overall translations and rotations of this molecule. So in order to see what representations the vibrational modes fall in, we actually need to remove those rotations and translations.
Can I ask a question?
Yeah, sure.
Could you repeat what we meant by A1 and A2? I've forgotten.
So A1 and A2 are different irreducible representations of S3. So A1 here is just a different name for the trivial representation. That's why the character is 1, 1, 1.
Yeah.
A2 here is this even odd representation. So I'm representing all even permutations by 1 and all odd permutations by -1.
I understand. Thank you.
So I need to remove now translations and rotations. And translations, well, that's a vector. So that vector is going to transform exactly according to this 3D representation that we had here. So I need to remove that. So removing translations, which is this 3D representation, and I know what the character is. So the character for this vector of E is 3. For sigma, it's +1, and for rotations, it's 0. So I can do exactly the same now to find out what irreps this representation contains. And if I do it correctly, I will find that this representation it contains A1 ones, and it contains E ones. Rotations, on the other hand, so removing rotations, that's an axial vector. So it changes sign for reflections with respect to the vector representation. So its character is actually going to be 3 there. Chi of sigma is going to be -1, and chi of c is going to be 0 as well. So this tells us that the raw A, that's A2 plus E, after doing all of this framework again with taking the inner product and so on. So in order to remove both translations and rotations, I need to remove 1 A2, 2 E's, and 1 A2 from this representation. So the vibrational modes are then going to be, let's see, what do we have left? We have 2 A1s left, and we have 2 E's left. So this tells us that for ammonia, we are going to have 6 vibrational modes, or 6 vibrational frequencies, but 2 of them are twofold degenerate with each other. So essentially, we are only going to have 4 distinct vibrational frequencies of this molecule, because we have two-dimensional representations, and on those two-dimensional representations, the frequency must be the same. So that's a conclusion that we can take from this. Any questions?
I have one question.
Mm-hmm.
When you say that we remove the translations, could you show what we practically do? I don't really understand what that.
Yeah. So I mean, here, if I look at this this ammonia molecule, what I'm looking at is, or rather, the vector space I'm looking at the representation of the symmetry group at is one where I'm looking at all of the small displacements of the individual atoms, right?
Mm-hmm.
So if I make an overall translation of this atom, that's going to correspond to all of these being the same, right? So like this. That's not the vibrational mode, because it's just translating the entire molecule. So this 12-dimensional vector space is going to contain not only vibrational modes, but it's also going to contain the translations. And in the same way, I can have something like, yeah, rotations like this. I can rotate in, well, essentially in 3 dimensions, and that's going to relate all of these displacements to each other. And so if I only want the vibrational modes, I have to take away the translations and the rotations from this 12-dimensional vector space. That removes in total 6 degrees of freedom.
Okay, thank you.
I mean, what I could have done is that I could have said, well, I'm only going to look at molecules that are not rotating and that are in the center of mass frame. So that would remove 6 dimensions from this vector space. It would be rather involved relations between all of those displacement vectors then, but it would be a 6-dimensional subspace of this 12-dimensional vector space. Okay, we are running out of time. just let me mention briefly before we stop that I mean, here we had that these would be the vibrational modes. Let's think about what would happen if I broke the symmetry here. So let's say that instead of having this ammonia molecule with all of these hydrogens being equivalent, let's say that I introduce here a hydrogen isotope. So I can take 2H and put it in one of the positions. In that case, I would break the symmetry. I would no longer have this rotational symmetry. I would no longer have, well, I would have a reflection symmetry left, but I will not have this rotational symmetry. So what that would do is that since I do not have these, this symmetry anymore, in general, if I have what was an irrep of the total group before, the remaining symmetry group here, which is only like the reflections in that axis, that's generally going to break this this irrep into two different trivial representations.